Okay, so I want to focus a little bit more on search trees. Okay, now remember what a search tree looks like. Each you have kind of a each node has a key that you can look for, right? And then everything that's smaller, I'll call the key K here. Everything here has going to be less than K, and everything here is going to be greater than K. Okay, now I actually want to make this a little bit more precise because it's not really useful to just ask, hey, is the key 20 in the tree? Okay, what we really want is to have a key and a value, and that way we can do better lookups. Okay, more useful lookups. So for example, the key could be a variable name. Okay, so the key could be something like A, B, C, and so on, and then the value could be like 1, 2, 3, and so on. Okay, so that's a legitimate possibility, right? And so I can store something that says, for example, C is actually equal to 3, right? And then I can do a lookup for C, and I'll get the value 3. Okay, so that's the way, for example, that you might store a memory for a program, right? Because a program has a bunch of variables, and each variable has a value at any given point. And so you want to know, what is the value of X right now? What is the value of I right now? And so on. And a binary search tree will do that for you. Okay, so that's a pretty common setup. Okay. Now, we're going to assume that the keys are distinct, okay? The reason for that is because if I want to put in X, and I have two X's in the tree, then when I say, what is the value of X, I wouldn't know which one to give you. Is it this one or that one, okay? So let's just make the assumption that the keys are unique. And that's actually not hard to enforce, so I'm not worried about that assumption. Okay, so here's how we might do a lookup, okay? So if I'm looking from an empty tree, okay, then the answer, of course, is just nil. Okay. Now let's say that I'm looking for K, and the root has K and then some value, right? And then we have a left and a right. Well, since I'm looking for K, then I'll just take that value and return it. I found it. Okay. It was at the root, right? Otherwise, suppose that the root is actually equal to K prime, right? And I'm looking for K, which is smaller, right? Well, what I'll do is I'll just look for K right there, when it's less than K prime. And if it's bigger than K prime, then I look for it here, right? When K is bigger than K prime. So this kind of captures everything, right? And we can now use that to actually do, implement lookup in something like, say, ACL2. Here's another version of this same code, okay? And you may like this one better. This is simply the one that treats it all like one formula, okay? It's closer to the style of ACL2. I'll actually ask you to do this one in the project as well, so you can always refer to this slide if you want some help while you're doing it. Okay. Now, what about insertion? Insertion is pretty similar. Suppose that I want to insert a key value pair into an empty tree, right? Well, if it's an empty tree, then I just return the root, right? I just create a new root that has that key and that value, and no children, right? Otherwise, well, here's a possibility. It could be that I'm trying to insert into, in this case, I'm trying to insert into the key that I'm looking at in the root. Okay, so for example, my root says that X is equal to 10, right? And here I am trying to add X15 into this tree. Well, what I'll do is I'll just erase the 10 and put 15 right there. That's the answer, right? And so the way that I do that is I build a new tree that has X and 15 and the exact same left and right children. Okay. What if what I'm storing is not equal to the root, but in fact has a key that is smaller than the root? Well, then just insert it into the left branch. And then here's the way to do that. We're going to build a new tree that has the same key and the same value or data as the old root, right? But the left branch is completely different, because it's what you get when you insert this new key value pair onto the old left branch. And the right branch doesn't change, because if it was smaller, then I know that I can only insert it to the left branch. The same goes for the right, for when it's greater than, right? Then it will put it into the right branch. And that's it, okay? That's the entire code for inserting into a binary tree. again, I can show you the other version of this, which is the one that instead of using the pattern matching for the left-hand side, just treats it like it was a well, just a single variable tree, right? Which is a lot closer to the ACL2. So again, I'm asking you to write this code in ACL2. So take a look at this to kind of get some inspiration, get some ideas, and then go off and write it. Okay, so that's lookups and insertions. Now, suppose that I add the nodes to the tree at random. Remember, we're most likely, right? We're most likely to end up with a beautiful tree, right? The odds are in our favor here. Of course, suppose that we add the nodes in alphabetical order, right? So we do something like this. First, we add an A, right? So we put that at the top. Then we add a B. Then we add a C. Then we add a D, and so on, right? This is actually the worst possible case, which is kind of embarrassing, because when we add something that is already in order, or reverse order for that matter, then we get the absolute worst possible behavior. So that's no good. Okay. Okay, most trees are beautiful, but every once in a while we get one that's absolutely ugly, right? That's kind of like getting a deck of cards. Most of the time, the deck of cards is completely shuffled, right? It's kind of like saying most trees are beautiful. It's got that same feel. It's a probabilistic feel. But every once in a while, someone gives you a deck of cards that's in order, right? And if you try to play poker with that, you kind of tell pretty quickly that something's wrong. Same sort of thing happens when you have a tree that's actually one of those very rare, very unfortunate trees that look more like a linked list. So it would be nice to be able to say with certainty, this tree is balanced, okay? So I'm going to give you an idea of balanced that is actually weaker than what we did before. Okay. Before, what we insisted was that all of the leaves were either at height h or h-1. That's really strict. Okay. So instead, let's take something that's a little bit more relaxed. And all I'm going to say is that the height of the left child is no more than 1 off from the height of the right child, right? So that if I look at the root and I look over to the left, I see that in fact, oh, there's, height 10. This one is height 9, right? I can't prefer one over the other by very much, right? So that's our notion of balance. And we're going to insert data into trees that are like that, okay? So here's the idea. Let's suppose that we actually have a tree that's mostly balanced in that sense that I just told you, okay? Now, let's add a new node, okay? So what could possibly happen? Well, a few things can happen. The first thing that can happen is that after I'm done adding the node and I look at my left and my right children, they have the same height. Okay, so if they do, I'm happy. I'm still balanced, and I move on. Okay. Now the other thing that could happen is that I insert my node into this shorter subtree, right? So yeah, his height could grow. It could grow by 1. Well, it's the shorter subtree, so that's actually okay, right? Maybe now it's even more balanced than it was before. The only problem that I get into trouble is when I'm going to insert into the taller subtree. So let's say that the height used to be 8 and 9, and now I insert something to the taller subtree, which is the 9 subtree, and now it grows by 1, it becomes 10. So now I have 8 and 10, I am no longer balanced, right? So that's kind of the only case that I have to deal with. So here's an example, okay? So I have, this is the key is B, okay? Okay, this is the key of the root. And I'm trying to insert something, and let's say that it's bigger than B, then it's going to go over on the left branch, and since this is of height h, and I'm sorry, I'm inserting something bigger, right? So it would go on the right branch. Since it is of height h, the worst thing that can happen is that it becomes of height h plus 1, but that's exactly what this is. This is h plus 1, and this is h, right? So if it goes into the right, I'm going to be okay, right? If it goes into the left, I could have problems because one of those could actually grow, and now it becomes h plus 2, okay? So let's try inserting, and let's see what will happen, okay? So I got unlucky. I went all the way down the left branch of the tree, and so now I have something that is too big. So how can I fix that? Okay, and here is the magic that makes this work. This is absolutely amazing. This is how we fix it. Okay, so what we're doing is we're starting here, and we're basically going to rotate this tree like that. Okay, so as I do my rotation, A becomes my new root. Okay, A is now the new root. Okay, and so B is bigger, so it actually becomes one of the children of A, right? It becomes the right child of A, and these things just get reshuffled. Okay, right? So this used to be the right branch of A. So think about that for a second. That was the right branch of A. So does this tree make sense? Well, that's bigger than A, right? It's still on the right side of A, so it's bigger than A, perfect. Okay. Now, it was the right branch of A, but B was on top of A, right? So that means that all of these things must have been smaller than B to begin with. And here they are. They're on the left branch of B. Perfect. Okay, so this is still a binary search tree. More importantly, if I look at this is of height h plus 1, and if I look at this guy here, it's of height h plus 1, so I'm balanced. Okay, so rotating the tree kind of in the opposite direction in which I insert it works. Right? So if I put something down my left branch, and it got too large. It can only get large by 1, so I will rotate it, and then it will work. It will go back to being the right size. Okay, that's awesome. Okay, now what happens if we, in general, okay, and here's what I mean. I only looked at the root, okay, but this is a huge subtree, and this is where I insert it. I don't have to worry about this branch here. That one's okay. But this guy could actually be not balanced. Now let me be very clear. Is balanced at the root after we do that shifting, okay? But what about the actual subtree, right? Because when I inserted it into the subtree, I kept going down the left-hand side, and so that whole subtree could have been kind of tilting to the left too much. The answer is really very easy. We'll just rotate at each individual node, not just at the tree, right? So whenever we insert that, at one node, we go down the left branch. Oh, the left branch got too big. Rotate. That's it. Okay? And then the parent says, well, I just inserted to the left branch. It got too big. Rotate, and so on. So I may actually have to rotate at each individual node all the way up the tree. How many of those are they? There's only log n, right? Because this is a balanced tree. So it means that from the root to the leaves is about log n. That's the beauty of balanced. So yeah, there's not that many times that I'm going to have to do that rotation, okay? So it just costs a little bit more than it normally costs to do an insertion, which by the way is order log n as well, because that's the height of the tree. So this is very efficient, okay? This is a very nice solution. If we insert to the right branch, then we'll simply rotate the other way. That's easy, okay? The one that's hard is when we insert to the middle of the branches, right? So if we look at this, this guy here is of height h. This guy here is of height h plus 1. But now I have this branch, which is of height h plus 2. That's because I inserted, and the way that it inserted is went left, right, okay? So, this is the insertion path. All right, so what can I do? Well, I can try to do the same thing we did before. Let's rotate. Okay, so I rotate it, right? And just as before, this becomes the new root. And the rotation goes like that. This is the old root, but now it's the subtree that's immediately to the right. Okay, now let's see. This is of height h. This is of h plus 1. Right? And then this part is of h plus 2. That didn't help at all, right? So it might seem discouraging. It's like this isn't going to work, right? But there is one remaining trick that makes this actually happen. And what we'll do is we'll take this tree, which we had earlier just kind of treated like this, h plus 1, okay? And we'll actually split it so that we have parts that are of size h, okay? And then we have a new root, okay? So now we'll rotate again, okay? And we'll rotate against the direction that we think we should go, right? So we insert it to the left, and we're actually going to rotate this way. Okay? But notice that this part is unchanged. Okay? So let me make that clear by bringing the old tree back. Okay? This is the part that we're going to rotate. Okay? And we're rotating against the grain. So X is going to become our new root. Okay? So X becomes our new root. A goes over there. And now let's take a look at the heights. This guy here is H, right? This guy here is H. This whole thing is H plus 1. So if I go all the way to the top, I see H plus 2. I haven't fixed anything, but I think you can smell the solution, can't you? Okay? Because now the next thing I'm going to do is rotate in the other direction. Okay? So this becomes our new root. Okay? Now remember what we had. We used to have V, A, and then X, right? So we rotated it once. Okay, we rotated the X here, and what that gave us was B, X, and then A, right? And then we rotated that again in the other direction to end up with X, A, and B. Okay, so we have to rotate twice, once in the direction in which we inserted, and the second time in the opposite direction. Okay, and if you look at this, they are all of height H plus 1. Every single tree that you see is H plus 1. So this worked beautifully. Okay, so that's well, that's the magic of this kind of tree. We'll always, as long as we start with something that's close to balance, meaning that the difference in height between the left and right subtrees are always no more than 1, then when I do an insertion, if I just remember to rotate after the fact, then what I get is yet another balanced tree. Okay? All right. I realize I did a lot of hand waving. Okay? This is not nearly as precise as most of our lectures, but that's okay, because this is actually a hard algorithm. It's most likely an algorithm you'll see in the algorithms course in 3020. Okay? It's a really nice algorithm. And at least you know of its existence. You know that there is a way to guarantee that insertion into a tree results in a balanced tree. Okay, and all we have to do is rotate, right? It's the same algorithm as before, with just those after the fact rotations at each node. Okay, all right. The name of this tree is actually AVL, and it's named after 3 Russian mathematicians who invented it. Okay, and well, their names are A, V, and L. Well, their initials are A, V, and L. So these are one of the most cherished trees insertion algorithms in computer science.